Hello everyone, my name is Yuhao Zhang, and I'm assistant professor with the Center for Power Electronic Systems at the Virginia Tech. So today I'd like to give an update of the progress of our member initiative project. And the title of our project is the Surge Energy Robustness of the GaN power devices and the modules. And specifically, we're going to focus on the application-driven evaluation and the physics of failure modeling for the robustness of the GaN power devices. And our team consists of the Virginia Tech and also the Lockheed Martin. Okay, so this is a quick review of our project, and the objective is to evaluate the surge energy robustness of the GaN power devices, and specifically to understand the withstand physics and the failure and degradation mechanisms. So we're going to test the devices under three different kind of the test methodologies: the single event test, the repetitive event test, and the test under the mission profile, which will be the aerospace application specific mission profile. And in the talk today, I will focus on our result on the single event test. Okay, let me first talk about the surge energy robustness, which is robustness highly desired for power devices, as it is essential in many applications, such as the motor inverters in the electric vehicles. Okay, so here I show the surge energy conditions and with respect to the device safe operating area. So basically, as you can see here, under the surge energy test, then essentially device often goes to the voltage which is higher than the rated voltage of the device. And this surge energy robustness of a device is often tested in unclaimed inductive switching test, the UAS test. So here shows the circuit diagram of the UAS test. So this is very straightforward. So the device on the test is put in series with the low inductors with the power supply. So the device is first turned on to charge the low inductors, and then the device is turned off, where all the energy stored in the low inductor has to go through the device on the test. Okay, the silicon and the silicon carbide MOSFET withstand the surge energy by avalanching, while a large amount of the electron hole pairs are generated by the impact ionization, and such a device can accommodate a very high current at the breakdown voltage, so they can dissipate the energy within the device. So the avalanche energy is a thermal limited like a parameter, which is very important for the power device ruggedness. However, for the gallium nitride power transistor, the high electromobility transistor, it actually has no or minimum avalanche capability because essentially there is no inherent p-n junctions between the source and the drain inside this device. So then the several questions for the GaN HAMs would be: the first one is how this device withstand the dissipated surge energy, and second one is what determines the withstand capability, and the third one is what is the failure degradation mechanisms under the surge energy conditions. And those are the questions we're going to answer in this project. Okay, so this slide talks about the device on the test and the test setup. So up to now, we have already tested two types of the mainstream enhancer mode gallium nitride HAMs rated around the 600 volts and the 30 amps. So here is the schematic of the two devices. And essentially, both devices have a p-type gallium nitride under the gate to realize the enhancer mode operation. There's a slightly difference. In one device, the gate forms ohmic contact with the p gate, and the other one, the gate metal forms the Schottky contact to the p-type gate. And essentially, to accommodate the various types of the devices, and then we implement the test setup by utilizing a universal like a motherboard, which accommodates the main power loops and the capacitor banks, as well as the daughter card for each type of a device, which accommodate the packaging and the gate driver of the devices. And also we designed the board to be able to measure the UAS at the higher temperatures. Okay, so here shows a representative withstand waveform. So the right line here shows the VD, and the blue line is the VG, and the green line is the ID. Okay. So essentially, there were four different phases, and the phase one is in device is on and inductor is charging, and the second one is a device is turned off. The third phase is really important. So this is the resonance between the low inductors and the device output capacitance. So essentially, you can see the device voltage just resonant to the peak value, while the current just resonant from the positive value to the negative value. And the positive value at the start of the resonance actually similar to the absolute value of the negative value at the end of the resonance. So this suggests very little resistive energy is dissipated during this resonance process. Okay, and when the drain voltage resonant to negative values, then essentially the device will turn on in its third quadrant. So then the device is on again, and the inductor will just be discharged by the power supply. Okay, so this slide talks about the failure of a device under the US test. So when we gradually increase the like energy in the inductors, then we can drive device to failure. And the failure is observed to occur at the peak transient voltage. And for example, like for the device from the company A, then after failure, like there will be a very large leakage between the drain to source, but the gate is still functional. Okay. And then we tested the peak transient voltage of the device to failure at the different low inductors. It should be noted that different low inductors actually induce a different period of the resonance or the different surge voltage durations. So from here we can see the peak transient voltage for failure doesn't really depend on the low inductors. So that indicates the device failure is solely determined by its transient breakdown voltage. And here shows the failure like analysis. So from the microscopic inspection, we found the device like we can locate the device failure locations, and then we can compare the failure locations with the electrical field distribution in the device. And what we observe is that the failure location is consistent with the peak electric field like location. So that suggests the like device failure is electric field limited rather than the thermal limited. Okay, so this is a summary of what we have found up to now. So basically, if we compare the silicon carbide MOSFET with a GaN under this US test, so the silicon carbide MOSFET withstand the surge energy by avalanching, and the GaN withstand by the LC like resonance and then the reverse conduction. So the energy is dissipated in the silicon carbide MOSFET during the avalanching process, while there is little or almost no energy dissipating during this resonance withstand. And the limiting factor for the silicon carbide MOSFET is thermally limited by the like avalanche energy, while that for the gallium nitride HAM is a purely electric field like limited and by the like transient breakdown voltage or the over voltage capabilities. And if you are interested in more details, and welcome to join like my talk on the Tuesday like afternoon, or read like our publications at the TPE and as well as the IRPS this year. Yeah, thank you very much.